All right, welcome back. So today we're going to switch topic a little bit. We'll go back to chapter 16. That's where we ended last semester, and we ended at the uh, oscillatory motion. But we'll finish this second half of of the chapter here on waves. Okay. So we'll introduce the concept of waves, and we'll talk about how waves interact with each other. Okay. So let's just jump in here. So you probably know wave propagates in either space or in a plane. So for example, if you generate a water wave in a pond, it will propagate outward, and then you see those crest and troughs of the waves, okay, going outward. And you might have heard also about the gravitational waves that a few years ago that been detected the first time. So two black holes merge and they create this massive wave and in time space, and then was detected by LIGO on Earth there. So wave is a disturbance that propagates and it moves from the place where it was created. Okay, so that's the definition of wave. And we, a lot of us like to do waves, right? If you go to surfing, so you surf on waves. And then if you go to a sporting event, sometimes you maybe part of this wave that created. Okay. One question to ask is, do you travel along the wave in the same direction? So when you are surfing, so do you also go with the wave, or you just crash over the wave and stay more or less in place? And when you are doing this wave with the crowd, hopefully when you stand up, right, you do not end actually the seat next to you, right? Hopefully that's not the case, okay? So the answer is you actually do not travel with the wave in the same direction, but perpendicular to the wave, you are going up and down, okay, in that case. All right, so let's take a look at wave. When a wave propagates, right? So there's a several peaks that you see on the wave. So a couple key quantities here, and that we'll deal a lot with is one is the wavelength we call lambda. So it's from position of the peak to the position of the next peak. That's called the wavelength. So the distance between two consecutive peaks. Okay, and the amount of the median. So if there's a bird here, it goes up and down when wave propagates through here. So the amount of the displacement of the bird, or in this case, like let's say the median, the water, up and down, that's called amplitude. Okay, so in this case, from the maximum to the negative maximum, two times of the x. Okay, so x will be just the amplitude, or more often we call it a for amplitude. The velocity of the speed of wave propagation, so that will be equal to the time or the distance travel from first wave peak to the next peak, and then the time it takes from for the wave to propagate from one peak to another peak. That's called actually period t. So if you do distance over t, that gives you velocity of a wave, okay? And 1 over t is frequency, so you can also do frequency times wavelength to find the propagation of the wave, okay? The speed of propagation of wave. All right. One particular speed of wave that we'll use a lot is the speed of the sound. So under normal ambient condition at room temperature about 20 degrees Celsius, the velocity speed of sound is about 343 meters per second, also about 770 miles per hour. Okay, so that's one thing. And then a lot of times you can just use 340 as an approximation. Okay, all right. When wave propagates, so there are actually two types of waves. Okay, so one is called the transverse wave, and then the other one is called longitudinal wave. Okay, so this is depending on the movement of the median in respect to the velocity of the wave propagation. So a transverse wave is where if the wave is propagating in one direction In this case, the slinky goes from left to right. And the median, the slinky, certain part of slinky itself, it's actually moving up and down. Okay, so for the median, it goes up and down, but wave travels through the slinky over here in the horizontal direction. So median and the wave's propagation are perpendicular to each other. It's called a transverse wave. Okay. On the other hand, if the median, so in this case, if you pull the slinky like on the sideway here, so it actually travels back and forth in the same direction as the wave's propagation in this case. Okay, so some part of the slinky will be close together, some part will be further apart. So in this case, the medium vibrate, oscillate in this direction, horizontal direction. The wave is propagating also in the horizontal direction. So then this is called longitudinal wave. Okay. So the displacement of the median is along the same direction of the wave motion. Okay. All right. Sometimes for a particular phenomenon to occur, you actually have both combine of the two types of waves. Okay. So for example, when someone plays guitar and then that sound get propagate to your ear when you hear it. So the first type of wave will be the oscillation of guitar strings. So that's going back and forth, but sound produced by that oscillation actually is going in the horizontal direction in the air. Okay, so so wave on the guitar it's actually a transverse wave, and then the sound wave in this case actually is a longitudinal wave. Okay, all right. So let's briefly introduction of waves. Now let's take a look if you have a couple waves when they meet, what happens? Okay. So when you have two waves, let's say this wave y1 going in this direction, and then there's another wave y2. Okay, so when these two meet, you can actually send the two waves in one same string. When they meet, then you can actually basically they will simply just add up. Okay, so then this one add up plus this one, it gives you this guy. A couple of special scenario if you have two identical waves when they meet. Okay, so then the amplitude will double if these two are identical. In that case, the resultant will have double of the amplitude. And if you have opposite phase waves, so that means when at the location that wave one has peak, then at that same location, wave one actually has a trough, okay, or valley in that case. So then positive here and negative here, they will cancel, okay. So the resultant then will be totally flat, okay. So kind of canceling out each other, okay. So if that happens, we call this destructive interference of the two waves, and then in the previous case, we will call it constructive interference of the two waves, so purely constructive interference. Many cases it will be in between. Okay, so either positive, constructive or destructive, but combination of the two. And again, just another scenario here. So two different waves when they meet, that's the resultant. Okay, so some part will cancel, some part will add up in that case. All right. So it's both constructive and destructive at the same time. Okay. When the two waves, if they are traveling in opposite directions in the same media, so let's say there's a wave here going to the right, and then this second wave going to the left. When they meet, okay, so they will simply add up, but after they meet, they behave like they never met. They are just propagating in their original directions, okay, in that case. The same here, when they meet, destructive, and then afterward they propagate onward as originally they are originally heading to, okay. In two-dimensional, if you have two-dimensional wave, so water wave is pretty much a two-dimensional wave, okay? So in that case, two-dimensional wave also interferes with each other. So again, if a peak from one wave meet a peak from the second wave, then they will add up. We call it constructive interference. If a peak from wave one meets the valley from peak two, wave two, then they will cancel out. Okay, if they are identical, they will totally cancel out. Okay, if they are not identical, then partially. So then you will have interference and destruction. You will have destructive interference and constructive interference happens. Okay, so in these cases, a peak meets a valley, so these are destructive interference, and then on these here, these are when peak meet peak, so they are constructive interference. Okay, all right. So typically, if you have two waves, they will come out from two sources. Okay, it depends on if, so let's say if at one moment source one gives out a peak on wave one, at the same time if source two gives out also the peak on wave two, then we call these as synchronized. Okay. On the other hand, if say wave one from source one, if it's a peak produced, and then on source two, the wave two has a valley or um, trough produced, then it's called out of phase. Okay, so in that case, but when waves coming out from these two sources, when they meet at certain locations, it just depends on if you have peak meets peak or peak meets valley. So then it will be either constructive interference or destructive interference. Okay. So if we look at it, a constructive interference, so that means a peak meet a peak or a valley meets a valley. Okay, so in that case, then the two waves they propagate at this common location. They have come through two paths, so path one and path two, so R2 and R1. And then if you take the difference of those two, so they should give you just multiples, integer number multiples of the wavelength. Okay, so that means if the two sources are originally in phase, so then if you have the path difference as multiples of wavelengths, integer multiple of wavelengths, then that means a peak meets a peak, a valley meets a valley. Okay, so in that case, n could be equal to 1. That means they travel the same path, or maybe 1 could be travel further, but by 1 wavelength. So then you still have a peak meets a peak in that case. Okay, or 2, 3, whatever integer numbers. So when you have that, you get constructive interference. On the other hand, if the paths of the two waves differ by just half of wavelengths, right? So if n equal to 0, that's 1/2. If n equal to 1, then that's 3/2. Okay, so just integer multiples of half wavelengths. Then you'll have a peak meet a valley, so then you'll get a destructive interference. Okay. Another scenario will be if you have two waves, they are actually their sources actually are in the opposite phase. Okay, so in that case, they originally have a difference of just when the first wave if comes with the peak, then the second one will be having a valley. Okay, so in that sense. So then the conditions will flip for destructive and constructive interference. Okay, so if the path difference is integer multiples of wavelengths, then you actually get destructive interference. And the other way around, you will get actually constructive interference. So the path difference is half of wavelengths. Okay. All right, so you have to be careful about for the problem if it tells you if the two waves are coming out of source of in phase sources or opposite phases are sources. Okay, let's take a look on the example here. So this one says two speakers, so the two sources with opposite phases. Okay, so opposite phases. So you want to make a note of that. This guy is named opposite phases. Okay, so then the conditions will be these two for destructive interference and constructive interference. Okay, because of that. So because of the opposite phase. Okay. And then they are positioned 3.5 apart as shown in the figure. So the two speakers, both pointing towards a wall 5.0. I think it should be meters. Okay, so the meters is missing, but it should be meters in front of them. An observer standing against the wall, midway between the speaker hears destructive interference. Okay, so initially this is midway over here, this observer. Okay, so then the path R1 and R2, they are the same. So this observer will hear distracted interference because it's opposite phase. Okay. Now it's asking you if this observer moved by 0.84 meters to the side, and he hears a constructed interference. So it's asking you what's the frequency of the sound emitted by the speakers. Okay. So let's take a look here. Um, all right. So when this person is over there, and so we can maybe draw a line down here, and here this distance 3.5. Okay, so wave one from the left hand side, let's call it that way. It will actually go that direction. Okay, so that's R1. Again, I'm drawing actually, I wanted to draw a straight line, but somehow this app will just give me a wiggly line, but just pretend it's a straight line, okay? And then this will be R2, okay? So again, should be straight, but it's wiggly. All right, so then because this is opposite phase, right? So then the condition will be R1 minus R2, the absolute value, and then from our figure, we know that R1 is greater than R2, okay? That should be equal to, so this is the first time he hears the distract interference, so that means n equal to actually 0 there, so that's the first condition of lambda over 2, okay? So if the second time, then it will be 3 lambdas over 2, okay? When n equal to 1, okay? Now, this is midpoint, okay? And then he moved by this. This is 0.84, okay, meters here. So then this line will be the 5 meters. Okay, so this guy is 5 meters. So we can calculate, so because this is halfway, right? So this is 3.5 over 2. Okay, so 3.5 over 2. And then this half is also 3.5 over 2. Right? So we can calculate this R1 because 3.5 plus that, right? Be this distance and the phi. So R1, so this is just R1 minus R2 equals to lambda over 2. And R1 is square root of 3.5 over 2 plus 0.84, right? Squared plus phi squared, okay? So that's R1 and minus R2. R2 will be square root of, now the other way around should be the 3.5 over 2 minus the 0.84, okay? And that guy squared and plus phi squared, okay? So that's your R2, and these two together should equal to lambda over 2, okay? So now you can calculate your lambda. Just calculate the left-hand side equation and then multiply by 2, okay? So it will turn out your lambda is going to be equal to 1.098, okay, or 1.1 if you would like, okay? That's your lambda. But it's asking you what's the frequency of the sound, okay? Now, to find the frequency, we know speed of sound is given. So speed of sound, it's actually frequency times lambda, or lambda times frequency, right? So then frequency should be equal to the speed divided by lambda, okay? So you'll probably use this quite often from this point on. So we can do 340 meters per second over the 1.098 meters, okay? And that will give you frequency. So F then is equal to 309.7, 1/2 but that's hertz, okay? So, or you can say about, this will be about 3.1 times 10 to the second hertz. Okay, so on that. All right, so that's that one. Now let's go back to the slide. Let's take a look at the mathematics of the derivation of the waves add up interference. Okay, so let's say wave one. So we know that wave goes like a sinusoid function, so we can use a sine function. Okay, so if you like, you can do a cosine. Okay, but sine kx minus omega t. Okay, because the wave function is as a function of time, it also as a function of position, right? So the wave goes, again, this is position, but as time goes, it's will behave slightly different. So it's a sine function. Let's say if we have two waves, they are both sine functions, and then they are offered by a little bit in this. This is called the phase difference. Okay. Um, delta small delta. So let's assume this delta is small. So when the two waves actually add up, okay, so y1 and y2 add up. So you just do mathematically, you have to do this two sine function add up. Okay, so sine of one function plus sine of second function. Okay, so that's one of the trigonometry identities. Sine of theta one. Theta one is this whole thing here. Okay, so this is theta one. And this whole thing here is theta 2. So theta 2 is differed by delta compared to theta 1. So sine theta 1 plus sine theta 2 is actually twice of cosine, the difference of the two angles, and then sine of the average of the two. Okay. And then in the cosine, it's the difference divided by 2. Okay. So that's one of the trigonometric identities. So use that. Then y1 plus y2 it actually becomes, because the difference is delta, right? So delta over 2, and the average will be because they are both kx minus omega t. So then you should have 2 of that, and then minus 2 of omega t, and then divide by 2. Okay, and then plus delta over 2. Okay, so the sine function is still there, but with a different phase shift of just delta divided by 2, and then cosine function is there. Okay, so if your delta is 0, that means the originally two waves are identical. So then delta becomes 0, cosine of 0 is 1. Okay, so then this y1 plus y2 becomes 2a sine. So this is 0. Okay, of the original sine function. So you can see that amplitude actually doubles. Okay, so that's what we mentioned earlier. So if that's the case, the two waves will add up. Okay, so then you get constructed interference of the two waves. Okay, and if delta is equal to 180, in that case, the two waves are opposite in phases. Okay, that's when we call it. So if they are different by 180 or pi, we call them opposite in phases or out of phase. Okay, so that means one wave will have peak, the other one will have a valley. So the two will actually cancel out. Okay, so 180 in the cosine function, if we look at previously, if 180, then cosine 90 in this here. Okay, so then this becomes 0. Okay, so then it will cancel out completely. Okay, so it's out of phase. So the resultant will be a distracted interference. Okay, all right. Let's take a look on this one. Okay, so it says two waves with same frequency, wavelength, and amplitude are traveling in the same direction if they um, differ in phase by 90 degrees and each has an amplitude of 4. What's the amplitude of resultant? Okay, so the two add up. Okay, so we'll be looking at this here when the two add up. This is the result, so we'll copy that down, and it says delta is equal to 90. Okay, so in this case, let's move to the second one here. So we'll say, okay, so y1 plus y2, because they have the same, well, let me just copy this one first. Okay, so equal to 2a cosine of delta over 2. So this is your new amplitude and sine of kx minus omega t plus delta over 2. Okay. All right. So when it says the same frequency, so that means f is the same, and then wavelength and amplitude. Okay, amplitude is a. Now, the frequency is related to angular frequency. Okay, so if you do omega is actually equals to because it's angular frequency, so 2 pi times f. Okay, and k is called wave number. Actually, is related to lambda. K is actually equal to 2 pi over lambda. Okay, so you might want to take notes on these two. Okay, for omega and k, they are related to frequency and also wavelength. Okay, all right. So it says delta equal to 90, delta equal to 90 degrees. Okay, so then in this case, this is still a sine function, so it's a sinusoid wave there. The new amplitude will be that guy. Okay, so for the new amplitude a prime, then it's actually 2 times our original a cosine of 90 degrees over 2. Okay, so you can put in there 2 times original amplitude is 4.0, and then cosine of now 45 degrees. Okay, so the new amplitude here will be 5.66. Okay, so will be increased a little bit. Okay, um, now it says for what phase difference will the resultant be equal to actually 4 original one. Okay, so that means you still want this a prime to be equal to the 4, which is the original a. Okay, so then we can say, okay, so this is the delta that you wanted to see what's this new delta would be. Okay, so a prime is still a, so we can say a equals to a cosine of delta over 2. Okay, so that a and a will cancel, so that means cosine of this is equal to 1/2. Okay, and if you remember, if cosine of angle is 1/2, the angle is going to be 60, right? So if you remember that, so that means, okay, my delta over 2 is actually equal to 60 degrees. Okay, if this is equal to 1/2, so then my delta will be twice of 60, will be 120 degrees. All right, so that's how we can solve for this one. Okay, so let's go back. All right, so briefly, what we learned today, we talk about waves. Okay, so a few key quantities there: wavelength, period, and speed of wave. Okay, and then we also talk about superposition and interference of waves. So basically, when two waves meet, they just mathematically add up. Okay, and then we also look at the details of mathematics there. Okay, we'll stop here today, and then we'll come back next time. Okay, see you guys.